Hello everyone. In the next few videos, I'm going to go over in great detail one of my favorite topics in 3D math, which is 3D rotations. Now we've already seen these elemental axis-aligned 3D rotations. So for example, if I was going to rotate around the z-axis, I would hold the z-axis fixed and then rotate it in the xy plane, which actually looks a lot like the ordinary 2D rotation, except now we got a z-coordinate hanging along that doesn't change at all. I could do similar things rotating around the x-axis, hold the x-axis fixed, rotate in the yz plane, or even rotating around the y-axis, hold the y-axis fixed, rotate in the xz plane. So those rotations are all pretty simple if these are my axes, if my axes are aligned with my canonical basis vectors in 3 dimensions. But things get a little more complicated when we compose these rotations together, so when we do one rotation after another. That might not necessarily be a rotation around one of these canonical axes. So I've created here what's called a gimbal system, and I'll provide a link to this in the description. I would encourage you to play around with it. So what this gimbal system is, it's a system of 3 interlocking rings, that each of which rotates on its own. So this outer blue ring here, I call yaw. This is rotation about the y-axis. And so that's holding the y-axis fixed and then rotating the xz plane. Just to check with my right-hand rule to make sure this is all kosher, if I put my thumb in the direction of the y-axis, then the counterclockwise direction should be going like this. And indeed it is, okay? Now, connected to that blue ring, so as the blue ring moves, there's another ring that's connected to it, this orange ring. But that orange ring can rotate it on its own. And that ring rotates about the x-axis. We call that pitch. So again, if I check my right-hand rule, if I put my thumb in the direction of the x-axis and curl my fingers on my right hand, then I see it should be sort of coming towards me as I increase, and it is. Okay. So here rotating in the yz plane, coming towards me. And then finally, actually connected all the way on the inside, so connected to the orange ring, is this green ring. And so we call this roll. This is rotation around the z-axis. Now remember, positive z in this right-hand coordinate system is coming out at us. So if I put my thumb coming out at me, then I should see that it rolls to the left. Let's see about that. Okay, there we go. But interesting, so this is actually connected to the orange one, and the orange one's connected to the blue one. So notice when I rotate the blue one, it rotates all 3 of them. When I rotate the orange one in the middle, it rotates the orange one and the green one connected to it. If I rotate the green one, it just rotates it by itself. And what I've done here is I've attached a plane to the inner ring here, because oftentimes these kind of systems are used, these 3D rotations are used to describe aeronautical things. Okay. So, a couple things I want to point out here. One of them is that, as I rotate all 3 of these together, I maintain the shape of my plane. So what I mean is the plane doesn't stretch, shear, or flip. And so what that means is I'm preserving this right-handed coordinate system as I go along. If you remember, one way to describe any matrix is by describing what the x-axis goes to, what the y-axis goes to, and what the z-axis goes to. And that will end up being a vector described by the first column, second column, and third column, respectively. So for example, in this particular choice of angles here, I end up with this vector in the first column, so that's going to be my new x-axis. And that looks right because I see it's certainly pointing to the right, it's pointing a little bit up, it's actually pointing a little bit towards me. My new y-axis, okay, that's actually pointing a little bit to the left. Let's see it's negative there. But still pointing up and still pointing a little bit towards me. Actually, okay, here it is aligned with the bottom. So before I go too much further, okay, so I want to point that out. It keeps, the matrix is always going to describe this right-handed coordinate system where each column has a length 1, so no stretching. And the columns are all mutually orthogonal to each other, and this remains as a right-handed coordinate system, so no flips. So anyway, okay, before I go too much further, let me just come up with let me convince you why this composition of rotations described by these interlocking rings looks like this. So I'm going to go back and I want to make a scene graph of this, actually. And so on the outside, I have this first ring. Okay, so in the coordinate system of the first ring, that's the yaw ring. That's the one that rotates around the y-axis. So when I look at that, let me get my arrow here. When I look at that, that is going to be, again, the rotation around the y-axis. Okay, now connected to that is the inner ring, which is pitch. That's a rotation around the x-axis. So to get from the coordinate system of this blue ring to the coordinate system of the orange ring, I rotate around the x-axis. Okay, so that's relative to the blue ring. I rotate. Okay, now if I'm in the orange ring, that green ring is connected to it. And so to get from the orange ring to the green ring, I do a rotation around the z-axis. Okay, so this tells me how to get from one to the next. And then at the end, there's some kind of translation. You know, the plane is attached to this ring. So there is one more thing before I really display the plane here. But I want to focus on these rings here. So if you remember our rules for scene graphs, we go from the top to the bottom. And the transformation that takes us then from the bottom to world coordinates is just stacking these matrices next to each other, going from top to bottom. So I have, okay, start at world coordinates, I go ry, rx, rz. And it's that multiplication that will take me from the local coordinates in this green ring to world coordinates. So that's how I'm going to be able to display, that's how I know how to display the green ring in world coordinates. So that's all the way at the bottom here. If I wanted to display the orange ring in world coordinates, it would be ry, rx. So that's actually what I'm doing in this animation here. And then if, you know, of course, if I wanted to display the blue, it's just ry, that's all. Okay. So hopefully that convinces you why it goes y first, x first, and then z after that. So just to tell you, this is not the standard choice. So here's a Wikipedia page showing there's actually 6 different orders that you could put these rings in. I've chosen this one here, so y, alpha, x, beta, z, gamma. The standard choice actually puts them in the reverse order from how I have them. I just felt like it made more sense to connect this yaw ring to the floor. so that's why I did it. I just felt like the ring that, you know, the axis that was the y-axis would be attached to the floor. So I put them in the other order. But just to tell you, I mean, it all checks out. So you see, actually, if you want to go into gory detail here, you can actually multiply these matrices together, and you get this god-awful thing. So you could do that if you multiply these 3 matrices together. Remember, any composition of matrices can be represented as a single matrix. So, and I'm abbreviating this here. C alpha is cosine alpha, you know, S alpha is sine alpha, etc. So this is actually the one matrix that describes everything. But I think it's a lot easier when you break them down into these pieces here. Although I'll return to the big one in a moment. Okay. So the thing I want to talk about now is, what does this have to do with animation, which is the unit that we're ostensibly in right now? Okay. So if I start these gimbals at a particular position, and then I ask to move them to another position, let's say this, then my plane goes like that. Okay. Actually, let me move them a little bit further. And so, okay, what am I actually doing here? So this is an animation that takes me from the plane pointing forward to the plane pointing in some different direction according to where the gimbals end up. And you notice I'm moving the sliders along here, and I'm moving them at a constant velocity. Okay, so the alpha, beta, and gamma are all increasing at the same rate the whole time. So the way that I would write that as an equation, so I'll call this here. This is so technically these are called Tate-Bryan angles, but I'll call this yaw, pitch roll, angle linear interpolation. So what I'm saying here is, okay, if I want to do an animation from a set of these angles, so alpha, yaw, beta, pitch, gamma, roll. So we'll say if I want to go from alpha 1, beta 1, gamma 1 to another set of angles, alpha 2, beta 2, gamma 2, then the equation for that, I can create a parametric equation for that. I can say, all right, well then I'm going to define some alpha, beta, gamma as a function of time. So we'll say, okay, I have an animation now. I want to imagine that my animation is going from time 0 to time 1. And then the equation that I'm going to get is going to be alpha 1 times 1 minus t plus alpha 2 times t. So let me just start with that, because the other two are going to be the same. Okay, so just to show you here, if I plug in t equals 0, this is going to start at alpha 1. If I plug in t equals 1, that's going to go to alpha 2. And then it's the same exact thing for beta and gamma. So you start at the first one, and you go to the second one at a constant rate. So this is called linear interpolation. So we're doing linear interpolation of these three angles to get me from one starting point to the other. All right, so I can choose, I don't know, let's choose another orientation here. Let's say I had the plane pointing like this. And so here, okay, so they're sort of pointing up in maybe a little weird direction. Start at the beginning, and that's how I get there. Okay, so fine. Let me get rid of the gimbals, and you can just watch this go by itself. Okay, so that's apparently how I can get from the starting rotation to the other one. But something a little weird is going on here. So let me move these through the entire circle from 0 to 360. I'll move all these axes like that. So if you watch this plane carefully, you'll notice that it's kind of jerking around a little bit. It's not always moving kind of in a smooth way. If I take the gimbals away, it might be even more apparent. Okay, so see how it kind of almost stalls out there? And now it kind of goes even faster. So there's something weird happening around 90 degrees in pitch, and also in 270 degrees in pitch. Okay, so let's look at 90 degrees first. So when I set the pitch to 90 degrees, what ends up happening is that the yaw axis and the roll axis are doing the same thing, but in reverse. So the yaw and the roll are working against each other. Okay. That's why it slows down a little bit going through 90 degrees. On the other hand, when I set this to 270 degrees, yaw and roll are working with each other. So this is not usually the case. Usually, I mean, if I put this to a different angle that's not 90 or 270, I mean, yaw and roll are going to move the plane in different directions, right? They're not going to move the plane and rotate across the same axis. But something weird happens at 90 degrees and 270 degrees where they're actually rotating in the same plane. So yaw and roll are actually, so the inner and the outer ring are rotating my object in the same plane of rotation. At 90 degrees, they're working against each other. And at 270 degrees, they're working with each other. So at 90 degrees, it goes slower. And at 270 degrees, it goes faster. And near those angles, it gets messed up too. So when I look at this whole animation, I just see a lot of kind of jerking behavior. It's not moving in a smooth way. So this is a phenomenon known as gimbal lock. And it's just a thing that happens with gimbal systems like this. So, I mean, the good thing about gimbal systems is we can reach any possible rotation that we want in 3D with these. So given a possible rotation, so give me a right-handed coordinate system, put it, in some orientation, I will be able to find an alpha, a beta, and a gamma. Not necessarily unique, but I'll be able to solve for an alpha, a beta, and a gamma to move you there. The problem is, when I interpolate between the two, it can get a little wonky when I'm near or at gimbal lock. So to show you why, I do actually want to go back to this super messy matrix for a second. And notice that, okay, so what's happening at gimbal lock? So again, we said that, let's just look at 90 degrees for now. So let's suppose beta is equal to, we'll say pi over 2. So that's 90 degrees. Well, in that case, cosine of beta is 1. Sorry, cosine of beta is 0, and sine of beta is 1, positive 1. Okay, so cosine of 90 degrees is 0, sine of 90 degrees is 1. And so if you substitute that into this messy matrix that describes the whole gimbal system, it ends up simplifying quite a bit. So, every time we have a sine of beta, we just replace that with a 1. Every time we have a cosine of beta, it actually drops out and is a 0, like that one. So that drops out, that drops out, that drops out, that drops out. So we got those 4 dropping out. And then every time there's an S beta, we replace it with a 1. So you look at this matrix, this looks a little more like just a 2-dimensional rotation, right? So if I held my beta fixed, I'm not actually getting anything different happening between alpha and gamma. And in fact, if you go back to your cosine sum identities and your sine sum identities, what you'll see is this simplifies to this matrix here. So we see, yeah, alpha and gamma are fighting each other, rotating around a plane, in a plane. So that's how you can see it mathematically. So this is called gimbal lock. So gimbal lock is also definitely a problem from the point of view of a camera that's going through a sequence of rotations. And so this is definitely the kind of thing you might want to do in an animation, like start with a camera that's like maybe up here looking down, and then choose another camera and kind of put that in a different position, maybe down here looking up or something. And so I can ask you to go from one camera to the other, and let me do that by interpolating the angles in some gimbal system that would realize each camera. And so here's what would happen if I did that. So I get this kind of animation. What I'll show you, what I'll be working towards in the rest of this module is a better way of doing this. That should be a little bit smoother the whole time. And I'm not sure how easy it is to see it here, but this one kind of does that wonky thing where it pivots up, and this one is smoother the whole way. That's the idea. Okay, there's one more thing I want to show you mathematically about these matrices before we move on to something better. Even though these have a problem, there is something very cool about them, which is you can solve for any rotation matrix. You can solve for the angles that would be needed to realize that matrix. And so what I'll do here is I'll create a random rotation matrix in Python here. So for those of you who have seen it before, I'm going to use something called the singular value decomposition to decompose a random matrix into 2 rotational parts and a scaling part, and I'm just going to look at the 1 rotational part that I get. And if I look at this, I will find that okay, each column sums to 1. The sum of the squares of the entries of each column is 1, which means they're length 1. So let's just check that. So these should all be 1. That's great. And then also, every column should be perpendicular to every other column. I can do that actually with a matrix multiplication by this thing with its what's known as a transpose. That's switching the rows from the columns, and that should give me approximately identity matrix, which is very close to it. So yeah, 1, 1, 1, and these are basically 0. Okay, that's good. And then it shouldn't be doing any flipping. So I can check that with something called the determinant. And I get, whoops, I meant to say lineage.determinant. Okay, that gives me a positive number, should be 1, approximately 1. Okay, so these things are all, this is a valid rotation matrix. But how do I figure out, I would like to twiddle these axes here until I somehow get these 9 numbers to agree with these 9 numbers. How do I do that? Well, let me go back to this god-awful equation, because it's actually going to help us. Actually, not this one, the full general equation. And so if I bring this back down here, we can look at it and pick out a few terms that'll help us. And so one thing I see right off the bat is that, okay, beta is isolated by itself in row 2, column 3. So what I can say here is that, so maybe I'll call this R here. My rotation matrix R is equal to that. And so I'll solve for beta by saying, okay, well, if I take the negative of R at row 2, column 3, and then I take the inverse sign of that. So the arc sign, or the inverse sign function, then that will give me beta. Okay. So let's check that. So we'll try that in a second. Okay, that's nice. Another thing that you'll notice is if you take the quotient of this first row, third column with the third row, third column, then this C beta will cancel out and you'll get S alpha over C alpha, and that's actually tangent of alpha. So what you can see is actually so that the ratio of the first row, third column to the third row, third column is the tangent. So that means then that it's the tangent of alpha. So that means then that alpha is going to be the inverse tangent, tan of -1, inverse tangent of R13 and R33. Now I'm being a little bit careful here actually. With the inverse tangent, you always have to be careful because if you divide a negative by negative, I can't tell that from a positive or a positive. So I actually want to keep these as two separate arguments. Okay, so that's that, and then actually we've got a similar thing going on with gamma. If we take the ratio of row 2, column 1 with row 2, column 2, we're left with S gamma over C gamma. And so that would be the inverse tangent of the quotient of those two. That's what gamma would be. All right, so there's the equation. Let's try these equations out on our little example here. So if I were to say beta is equal to arc sine, that's the method in NumPy, negative R, and I'm 0 indexed in my matrix, so instead of 2, 3, I'm going to say 1, 2, the second row, third column. And let me also, arc sine is going to return radians. My program expects degrees, so I'll do that. Let me now do alpha. Now here I'm going to use this method called arctan2. That's the version of tangent that takes 2 parameters, so it can tell what quadrant you're in. It doesn't get the first and third quadrants of the 2 positives mixed up, or it doesn't get the second and the fourth quadrants with the 1 and negative positives mixed up. It can tell those all apart. So that's going to be first row, third column, third row, third column. That's arctan2 for alpha. And then finally we got gamma, second row, first column. And then second row, second column. All right, let's print them out, alpha, beta, gamma. And I noticed that alpha and gamma are negative. Let me just add 360 to them. That won't change. It'll go a full 360. But my program is expecting these to be between 0 and 360. Okay. So 343, 5, and 240. Let's try it. So 343, 5, 240. So supposedly this is the random rotation matrix I came up with. Doesn't look like a particularly pleasant position of the plane, but is it right? So negative 0.46, yep, 0.84, negative 0.29, yep, that looks like it. Okay, so there you have it. Given any right-handed coordinate system described as a matrix, a rotation matrix, I can give you these angles in the Gimbal system I created here to realize that. So now we'll move on to some other representations. I'll just have you do a quick little exercise implementing the same kind of thing in JavaScript.